The broadcast is now starting. All attendees are in listen-only mode.
I'd like to welcome everyone who's joining us online to the latest MASTS Webinar Series. Today we're joined by Dr. Susan Gallen, who will be presenting a talk on, as you can see, the moult in southern elephant seals. Susan is an honorary research fellow based at the Centre National de la Recherche Scientifique in Strasbourg, and apologies for my pronunciation, where her work focuses on the behavioural ecology of pinnipeds, and in particular the foraging ecology of southern elephant seals. Hope I got that right, Susan.
Yes.
As many of you are no doubt aware, Susan also participated in the MASTS Postdoctoral and Early Career Researcher Exchange Programme, where she worked alongside Dominic McCafferty at Glasgow University, looking at the energetics of huddling during moulting in elephant seals. On a more practical note, if any of you have any questions, online audience have any questions for Susan, if you could please click the raise a hand button on the left-hand tab of your menu. This will let us know that you have a question or comment, and we can then unmute your microphone at the end. Or alternatively, you can type your questions under the questions tab. So without any further ado, I shall hand over to Susan, who can begin her talk. Thank you, Susan.
Good afternoon. So today I'm going to talk about the moult in southern elephant seals. And before I start, I would like to thank my co-author. I would like to thank Caroline, who is the PI on that project. I would like to thank Andre for the help and support. Camille, who collected the data and did the analysis for the GPS data. And Dominic, who introduced me to the world of thermal imaging. And I would also like to thank MASTS, who provided the funding for me to spend some time with Dominic in Glasgow this summer. So, yeah, it's working. So I'm going to start quickly with an overview, giving you some background information on southern elephant seals, on moulting and thermal imaging. I'm going to give you the objectives of our study, and I'm going to present our main two study, our Transect study, where we looked at the temporal and spatial pattern of fallout behavior in southern elephant seals, and the individual resight study, where we follow individual throughout the moult. And then a few slides discussing our result and challenges and perspective related to our study. So a few facts about southern elephant seals. They are the largest pinniped species. Male weight between 1,500 and 1,300 kilograms. Female between 400 and 600 kilograms. So they are an extremely sexually dimorphic species. Males are up to 10 times larger than the female. They are incredible divers. They do really long dives, up to 2 hours, but regularly 30-40 minutes or more. They also do really deep dives. The maximum recorded was 2,500 meters, but they regularly dive to 800 meters or more. While at sea, they are continuously diving, spending 19% of their time doing just that. They do 2 annual migration from their breeding and moulting site. So between this time where they're breeding and moulting on land, they are migrating at sea to feed. So there's a summer migration between the breeding and the moulting phase of the annual cycle. And then there's a winter migration between the moulting and the breeding phase of the annual cycle. They are also a major consumer of southern ocean biomass, and as top predator, they are a good indicator species of the health of the environment where they feed. So I just put a few pictures on the side here. So that's a big male that is easily recognizable with his big proboscis. That is just to show you the difference between the male and the female. That's just before the female returned to sea. She raised a quite healthy pup now, and you can see how big the difference in size is between the two. That's a female when she arrived, and she just had a pup. You can see she's much bigger and fatty. So there are 4 main populations of southern elephant seals all around the Antarctic continent. There's a population in Macquarie Island, which is just south of Australia. One in Kerguelen, which is south of the Southern Indian Ocean. There's the Patagonian population in South America, around Peninsula Valdez. And then there's the biggest population, which is the population from South Georgia, but that also includes population from the Antarctic Peninsula. The worldwide population was estimated in the mid-90s to be around 615,000 individuals, and it's a non-threatened population species. So while we have this quite distinct population where animals breed and molt, the foraging area overlap at sea. And for example, you can see animals from Kerguelen and from Macquarie Island all feeding around the Antarctic shelf, more or less like at the same places. Also animals from Macquarie and from the Antarctic Peninsula travel far in the middle of the ocean, certainly like in a specific oceanographic feature where they forage. So a little bit about the annual cycle now. So this is a graph showing you what southern elephant seals do throughout the year. And you can see that there's 2 phases where they are on land, rolling out. There's the molting phase and the breeding phase, and then the 2 migration that I told you about before, the summer migration and the winter migration. This does not mean that seals are molting for 3 months. It means that during that time seals are molting, but usually for female and for males, the molting phase lasts around 1 month. For the breeding phase, the breeding phase for female is 1 month or so, more or less. But for males, it can be up to 3 months where they're on land defending their harem to get access to female. So the time spent at sea is time spent foraging because they need to build energy reserve in preparation for this period on land where they're holding out during the molting and breeding and where they're not feeding. So the migration at sea can be really long. The winter migration can be 6 months or more and cover millions of square kilometers where feeding is often associated with frontal system, ice age zones, etc. So, and then we have 2 hauling out phase. So twice a year they go back to land to breed and to molt. The mass loss during the breeding for female, they can lose 31 to 40% of their body mass in 3 weeks. Male can lose between 26 and 46% of their body mass in 3 months. And during the molt, female invests half as much energy for replacing their hair as they do for their offspring during the breeding season. So I will quote FIDAC, and because the molting is just like only the cost of molting is only second to breeding, it seems fair to say that elephants look after their own skin. However, even though this is a really expensive part of their annual cycle, and an expensive part of the cycle that they cannot avoid because they have to replace their hair. There's been only 1 study to date that has investigated the energetic of the molting southern elephant seals, and that was done by Boyd et al. In '93. So I think that part of the life cycle needs some more attention. So the molt in most fossil species takes 3 to 4 months where they progressively replace their hair. Oops, sorry. In southern elephant seals, however, we talk about a catastrophic molt. That means that they have to replace their hair and their epidermis at the same time. So the new hair grow under the old hair, and little by little they shed the old hair, and that just like fall away, fall apart. So the epidermal cells of fossil seals require a minimum temperature of 17 degrees for growth, which is well above seawater temperature, especially for subantarctic species. And this is why they have to haul out to replace their hair. It's been studied that the optimal temperature for which epidermal cells proliferate is 37 degrees. So maintaining a high skin surface temperature, especially for southern elephant seals that go for a catastrophic molt, would minimize molt duration. The faster they do it and the better it is for them, then they can go back at sea and feed again. So for this study we've been using thermal imaging. Thermal camera, it's what we call an infrared camera, and it can determine the surface temperature of object or organism by using the physical laws of radiative transfer, and the difference in surface temperature is seen at different color on the image. And the great thing about that technique is that it's a non-invasive technique. You don't have to catch the animal, you don't have to manipulate it, you can just take a picture of it. So it's more and more used, and it's been used to investigate temperature regulation in a range of species. For example, in seals, Patterson et al. In 2012 used it to look at changes in surface temperature of harbor seals through the molt. It's used to study heterothermy and adaptation to the cold, thermoregulation, physiological stress and welfare. And it's also been used a lot to detect or survey animals in the dark. And in marine science, and in Scotland in particular, it's the most reliable method of surveying seals by air. So mammals have to balance heat dissipation with heat production to maintain core body temperature independently of the environment. Thermal balance is undoubtedly challenging for mammals living in subantarctic region, especially during the molt, and I would say especially for southern elephant seals that lose big patch of hair and have to replace it so quickly. So molting seals must cover the cost of growing new hair and epidermis during a period of fasting while the insulation property of the skin are impaired. So currently we have a limited understanding and knowledge of the process of the molting seals with respect to how much it costs for the individuals and within their life cycle. So there's been quite a few studies that have shown that the energy cost of the molt is only second to lactation. And in order to be able to model the energy demand of the seals, we require a big knowledge of that process and studying the heat loss from molting seals and how this may be modified by behavioral or environmental variable is important. So in this project we wanted to determine the temporal and spatial pattern of all-out behavior of southern elephant seals in relation to environmental conditions. We also wanted to look at the process of heat loss from molting animals and how this may be modified by behavioral and environmental factors. And finally wanted to look at if aggregation patterns, and in this we mean like huddling, they staying close to each other to keep the warmth in relation to both their body condition and environmental condition. So the study site for this project is Point Suzanne in the Kerguelen archipelago. So this is the island, and it's more or less 4,000 kilometers from Cape Town, Perth, or the South Pole. This is a close-up of the island, and this is Port-au-Français, the main research station, French research station in Port-au-Français, and this is Point Suzanne here. So if you can remember what I've told you before, Kerguelen is the second largest population of southern elephant seals behind South Georgia. So these are the different index or categories that we use for the studying the moulting stage in our study. So when we looked at the picture, we classified seals depending on how far they were in the moult. And when they started losing hair in the head or flipper, but they had still like most of their old hair, that was 20%. When you could see more patch of the new hair, but the old hair still covered more than half of the body, it was 40%. Then here, like you can still see patches of the old hair, but the new hair is more than 50% of the body, 60%. 80% is when there was a few patch around the seal's body, and 80% is when there was like the old patch of old hair left from the seal. So for example, in that picture, that seal there would be classified as being 20%. This one would be 60%, less than half of his old hair. This one would be more than 80%, just like a few bits there. And that one might be 100% completely molted. So for the Transect study, we looked at 3 different habitats: the grass, the beach, and the wallow. So we did 2 Transect, one on the grass and one on the beach, and then we had a quadra in the wallow area. So these Transect were done daily throughout the study. So during this Transect, we recorded behavioral data. That means the number of groups that we recorded during this Transect and the group size for each group with the number of individuals, and then we also looked at if animals were huddling or not. So a group is any animals that is within one body length of each other, and huddling means that the animals are touching each other. During this Transect, we also recorded environmental variables. So we always had a fixed automatic weather station near the feed hut, but we also take measurement of environmental variables with a handheld instrument during each Transect to have the local environmental data. And then what we call the energetic data set, where we recorded the stage of molt, living between 0 and 100%, as explained before. And then we used an infrared camera to take thermal images to obtain local surface temperature points of the seals. So for the thermal imaging analysis, we decided to use when we could 3 temperature points. So 1 temperature on the forehead of the animal, 1 on the back or the belly of the seal, depending on its position, and 1 on the hind flipper. But depending on like the group formation, we could not always have these 3 temperature points. We also decided to go for just points because depending on, again, the size of the group, the distance that we were to the seals, any bigger area would be more difficult to compare between photographs. So that's what we thought would give us the best data set that would be comparable between photos and groups. So for moulting individuals, we still recorded temperature point on the head and the back of the belly and the flipper, but we also recorded what we call a hot point, which is the new skin, and a cold point, which is the old skin. So here you can see just a normal photography, and you can see the new hair that is just growing. That's the old patch, a patch of old hair that is falling. You can even see that here there's another individual in the front. You can see that it's just starting to mold, and you can see that in the thermal imaging by the body surface being warmer. But as you can see, this one is not in focus because these were taken in picture. So yeah, this is on each picture that gives you a kind of range of temperature. For example, here this is a dark, is low temperature. Here is the grass, and then as it becomes clearer, lighter color means it's a warmer temperature. So for the analysis, we use the difference between the body surface temperature and air temperature that we call DT to examine changes in temperature of animal throughout the study. For the data analysis, we only used dry animal. That means that data or picture that were taken on rainy days, we didn't we didn't use this data set for the analysis. Also wet animals that just came out of the water from a puddle, we also didn't put them in the data set. And this is to show you how we can, how we try to identify wet animals. At the top, it's a picture taken during a rainy day, and you can see here a wet animal are quite easily recognizable, and that's dry animals. They're often quite shiny and wet. And you can see that on the thermal imaging just by also looking at the range of the body surface temperature, which is much shorter, much smaller than on a dry day, where animals are nearly in the 30s, while this one, the maximum was 24 degrees. But also, the detail, when a seal is nice and dry, the color is quite homogeneous on the seal, and you also have a good details of the head of the animals. Wet animals, in some way, they kind of look homogeneous, but you can see that the flipper is drying faster than the rest of the body, and the head, and mainly the head, is this really warm area that dry first, but you can't see the same detail as on a dry seal. So some data. So this is for the Transect, and you've got the number of individuals that were holding out either on the beach, the grass, or the wallow habitat during the study. So what is interesting? Well, first I have to explain that we didn't start the wallow Transect at the same time as the beach and grass habitat, so that's why there's no data here. But this year we will. And so what you can see that in the grass seems to be a little decrease at the beginning, and then quite stable number of animals holding out, and then an increase towards the end of the study. For the beach, they were quite low at the beginning. Here there seems to be higher number of individuals holding out, and then it decrease again. And what you can see for the water is that there was much higher number of individuals holding out. So that's what certainly is the peak of the moulting at least for the individual in that area. And then as the moult progressed, there's less and less individual. And here what was interesting is that I added the temperature, and by temperature I mean the atmospheric temperature, the air temperature, for the study, so that we recorded every day during the Transect. The red line here is the mean temperature over the time of the study. And what I thought interesting is that when the temperature was above the average for that time, early February, so at that time that there was more seals holding out on the beach. So that was one of the first interesting kind of results we got. So just we looked at then of the number of individual holding out in relation to the percentage of humidity, just to see how environmental variables might affect preference for certain habitat. For the grass, there's no pattern. Some seems that animals prefer the grass for certain day. And then this is the same, the number of individuals holding out in relation to the percentage humidity for animals that are holding out in wallow. Again, there was no obvious pattern. But for the animals that are holding out in the beach, it looks like when there was a low percentage of humidity, there was a higher chance of having more individual holding out in the beach. So that fits with the temperature pattern I just showed you before. It looks like when the temperature are higher and the humidity is lower, there might be a higher chance of finding individual holding out on the beach. So looks like that during the moult, seals use different habitat. Grass maybe at the beginning and end of the moult. Definitely wallow during the moult. That's where we found the highest number of individual holding out. And then for the beach, it's interesting because there was not many individual holding out in the beach, except on particular hot day or dry days. So it seems like there's an importance of maybe the characteristic of the substrate or maybe access to the water during the moult. As you can see, so here it's a seal holding out on the beach, and you can see that the surface temperature for the grass is quite low, much lower than, for example, when you look at image taken in the wallow, where it seems that the ground surface temperature is much warmer around the seals. For the beach, actually, yes, the beach, but as I said, like the beach is mainly made from stone, that seal seems to maybe use more on hot or dry day. It's actually quite warm because it looks like the sun is warming the stone. So I'm not sure if they're choosing this habitat in hot, dry days because the substrate is warmer, or because they get access to water, one or the other. So that's the number of transect that were done for the 3 different habitats, grass, beach, and wallow. So as I said, it was less for wallow. The minimum number of groups within each of these transect was between 0 and 27 for the grass. That means there were days where there was no seal in the grass on the transect, where there was always seals holding out on the beach or wallow in all of the transect, with maximum number of groups being 21 and 30 in wallow. The minimum number of individual for each of these groups varied between 1 and 12 for grass, so quite a smaller number of individual per group compared to more than 25 or 36 individual per group for wallow and beach habitat. So That's quite a big graph. I'm going to talk through it. It's a summary of the environmental variable and surface temperature measurement for the different body part of the seal holding out on the grass, the beach, or the water. So this total of here, total number of individual, it's the total number of individual for which we have a body surface temperature measurement. It's not the total number of individual holding out. It's just that on some of the picture there was ever the quality not good enough, or too many individuals in the group. We couldn't get always the temperature point for an individual. Then you've got the number of dry individual within each of these habitat. And then you've got the number of moulting individual that were found in each of these habitat for the Transect. And when I say moulting, I'm talking about seals that are obviously moulting, often are recognizable because they have this patchy pattern on them. You can see the old hair, which is colder than the new hair, which is warm. There might be seals that were at the beginning or finishing moulting that are not accounted for here. This is really counting the seals that are actually moulting, I would say. So only a few on the beach, 4 out of 168. 12 for the grass out of 291, and mainly 79, the highest number, is for seals holding out in the water. So that's where we had the most photograph of seals actually moulting. The environmental variables were more or less the same in the 3 different habitats. The other interesting point was that all temperature points for the different body parts where the temperature were higher for both the beach and the water compared to the grass. So that's interesting. It's at this stage we can't say for sure that like body surface measurement is surface temperature of body surface, what I'm saying, that the temperature of the surface of the bodies, the seal, are higher either on the beach or the water than the grass. It might be due of the characteristic of the habitat, because the substrate like keeps more the warmth, or so they lose less energy through the substrate, or it can also maybe means that they spent a different period of their moult in this different habitat, and if body temperature measurement change throughout the moult, then we don't know if it's if this lower temperature it's because we're taken either at the beginning or the end of the moult, or because oh, I'm going to start again. I'm sure I'm losing you here. What I want to say is that this lower temperature, we don't know if they link to a different phase of the moult, means either the beginning, the middle, or the end of the moult, or if they are linked to the characteristic of the habitat. I hope you got that. So anyway, we also looked at the effect of environmental variables of the measurement of surface temperature, and I did that just quickly for 2 different habitats. And not surprisingly, the environmental variable will influence a measure of surface temperature, like you have, for example, humidity and wind, and also solar radiation. But it seems that they don't affect the measure of surface temperature in the same way for the different habitats. So that's something we have to look further into. So without taking into account the effect of environmental variables on the measurement of body surface temperature, still wanted to look if there was a change in body surface temperature throughout the moult. So we looked at DT temperature, and if you remember, DT is the difference between the seal's body temperature and the air temperature. And we're quite happy to find that there seems to be a pattern, and that throughout the moult, it seems that the body surface temperature increase and then decrease toward the end of the moult. And that's for body surface temperature point taken on the head of the animal. If we look at the surface temperature point of the back of the animal, so it seems to have maybe a pattern, a little bit less in the flipper. You find again that pattern in the new hair. So what was the hot points? And again the hot hair. So that's good news, because we were quite worried that without being able to really take into account all the effect of the environment variable on the measurement of body surface temperature, we might not be able to see any of this pattern. But they are still visible, and it seems that there might be a peak in mid-moult, which is a result we're quite happy with for now, but for sure that needs to be continued and improved. So moving to the individual resight study. So we're still on Point Suzanne in Kerguelen, but this time we focused on specific individuals. So in 2012, we focused on 22 individuals. So we caught these animals, we measured them, we weighed them, and then we marked them with body paint and also with a seal hat, so we could follow them through their moult. So the aim was to catch these animals at the beginning of their moult, often like at stage 20% if we could. And then throughout the study, try to see them every time we could, every day, and look at the group size they were rolling out in, if they were huddling or not, position in the group. We also took a GPS position to see how they moved on land throughout the moult. 8 of them were equipped with GPS data, so we could look more into detail of their movement and land. And again, same definition as for the Transect. Group is within 1 body length, and huddling is when seals are touching. So again, environment data were obtained by a handheld instrument during the resight. And then the energetic data set. So we noted the stage of moult during each of the resight. We took again images with the infrared camera, this time to not only obtain local surface temperature points but also average surface temperature of different seals body part. And then body mass was obtained at the beginning when we caught them, and for 8 individuals we were also able to caught them at the end of the moult, so we had a body mass loss from the moult. So for the analysis, we chose the best picture from each sighting. When possible, we selected the profile one because this one is the best to look at temperature point because all the body surface of the seal is the same distance to the camera, and so it's a better measurement. We look at average temperature of the head and the body by delineating the area visible within the image. And the difference between mean body surface temperature and end temperature, DT, again the same as for the Transect, were used to examine changes in temperature throughout the study. So this is what it looks like. So during capture and recapture is quite nice because we've got nice picture of the seal on the profile, as I say. And that's what we do to look at the average temperature of the body. We just delineate the body and calculate the mean for this surface. So yeah, as I say, it's quite nice and easy capture and recapture. During the resight, however, sometimes the area of the body visible for the camera is not always ideal when they're in the middle of a group. So we knew that moulting occurred quickly in southern elephant seals because, as I said before, it's catastrophic molt. But we were hoping to have a little bit more time between the beginning and the end of the molt. By beginning, I mean when the animal visibly start to lose hair, so that's when we catch them, to when they have no old hair at all. They all replaced it. So often it happened within 10 to 15 days, which means that we had little time to follow them through the molt. And we also found variability in daily mice loss between individuals. So this table shows the different seal individuals. The number of observations means that some of these seals were only seen when they were captured and recaptured and never in between. Then the body mass at capture and at recapture, the number of days they were studied for, and then the total weight loss and daily weight loss. And what is interesting is that, for example, individual 13 and 15, that weight more or less the same at capture, and were followed for more or less the same number of days, lose different amount of body mass once, and quite a substantial difference. And it's the same for seal 8 and 16, for example, that gain weight around 280 kilo, are followed for 14 or 15 days, then like one is losing more weight per day. So it's just interesting to understand why there's difference between individuals that are the same size and which are experiencing the same environmental variables, because they're on land at the same time. So we also look at variability in movement on land and then see between individuals. And there was quite some variability. So here, I'm sorry, it's in French, but yeah, you've got the distance in meter on the vertical axis and different individuals. So there was 8 GPS deployed, but one was not recovered. So that's why we've got data for 7 individuals. And this is the mean distance in meter that the animal moved on land each day that they were studied for. And most of the animals didn't move too much, but for example, these two moved quite a lot. But if we try to see any relation between daily weight loss and mean distance per day, there's none really. You can see that 8 and 16 are the ones that moved the most, and they are the ones that were weighing more or less the same, but that don't lose the same amount of weight per day. In 13 and 16 and 15, quite a difference in daily weight loss, but low movement on land. So there's also a factor there that influence how quickly they lose and how quickly they use their body reserve that are interesting to look into. So in summary of our results, we can say that we found that moderation is quite similar between individuals and really short, but total body mass loss and the movement pattern are different between individuals. Looks like moulting seals prefer wallows, which we kind of knew already, and that seals rolling out on the grass on the beach are generally at the beginning or the end of the molt. But understanding why they prefer wallows, that's what we want to answer. Environmental variables might influence habitat preference, and that has been shown by the fact that on hotter and drier day we found more seals in the beach holding out. Body surface temperature of molting seals are different, like by a few degrees, than from non-molting seals. And new skin has higher temperature than old skin, so really thermal imaging technology is a great tool to study these animals during their molt, because the striking difference between these individual and throughout the molt. Again, non-surprisingly, environmental conditions influence the measurement of body surface temperature in different habitats, and that needs to be taken into account in the analysis. So the challenges for our study, so there's the obvious one, which is recapturing and retrieving the equipment, because molting seals do move a lot, and they're not that easy to follow and to catch again. The molting period is really short, and we're really hoping to get like this body surface measurement throughout the molt for some individual that would be followed, but it was much harder than before because it's such a short time, and that means we have to find these animals every day if we want to have like this, like a data point at 20, 40, 60 and 80% for body temperature measurement throughout the molt. So that's challenging. So just now we're working on a modeling approach to take into account the effect of the environment variables on the measurement of surface temperature. And then something else that that we've been working on, and that it's difficult, it's when we looked at our data set, we recorded the group size, contact, which means handling, not handling, and position of the group. And each of these factors might influence measurement of surface body temperature. Animals in a bigger group may get warmer, individual handling will get warmer, being in the middle or on the periphery of the group also will affect body surface temperature. And the challenge is to include all of them in a kind of super index of handling. So any advice or idea I really welcome at that stage. So what's next? Because as you will have seen by now, this is like an analysis of the first year of collecting the data, and there's still 2 more years to go. And it was really good to analyze this first year of data to improve and redesign some of the experiments. We've got a better idea of what we can do, what is achievable, and what we need to work on. So we're going to deploy more Argos and GPS tag this year, and also all animals will be fitting with VHF transmitters. Hopefully we can find them more easily. And then we equip some animals with Argos tags, especially for animals that will have a stomach temperature pill. Stomach temperature pill can record the temperature inside the stomach of the animals and are a good indicator of feeding event. So we just want to check if maybe some of the difference that we found between individuals' body mass loss is related to some individual feeding during the molt and some of us not. So the individual that will be equipped with stomach temperature pill and recorder will also be equipped with Argos tags, so hopefully we can get the tags back. iButton are really little tag that like really like little button as the name said, that will that record temperature. So we can put them to record surface temperature, but we also want to use them to look at if animals are huddling or not. So by putting this eye button around the flipper area, hopefully we can see when animals are in contact with each other, and we would have a kind of percentage of time spending huddling throughout the moult for some individuals. And then we hope to deploy also some accelerometers in 2014 and 2015 to determine daily activities and to relate that to daily body mass loss, and also to relate that to environmental variable. Do they move more when it's hot or cold or dry or rainy, etc. So the big picture for this study will help better understand the mechanism of thermoregulation in marine mammal. For example, why do seals prefer wallows when molting? Is it because the substrate is warmer? There's less deposition of warmth via conduction to the ground? Is it because of the physical characteristic of the wallow, like the mud and the rubbing with the ground and other seals increase the rate of loss of the old skin? Does the mud protect against heat loss or new hair patch? Or are they maybe at risk of overheating and need occasional access to water to cool down? So it's not so while this study will help better understand the mechanism of thermoregulation, we also want to link this molting behavior with at sea and breeding behavior. So that's not the name of this study, but it's just something that I think we should look to do in the future, because we found that body surface temperature vary through the moult, but we also found difference between individuals, like losing more or less body mass and different movement of the gland. So this individual behavior, molting behavior, would be nice to be linked to also maybe individual behavior at sea and during the breeding. And it's all about investigating fixed cost and flexible cost. And what I mean by that is, while it's important, it's important to look at to determine the energetic of the molting and to determine its cost for southern elephant seals. It's especially important because it's something that they can't avoid. While it's possible for a seal that is breeding to return to sea earlier, because, for example, if a female arrives on land to breed and have a pup and is in poor condition, she can decide to return to sea. She will jeopardize the survival of the pup, but she will make sure that she herself survives through another annual cycle. While when animals come ashore to the moult, they have to stay on land for the duration of the moult. So how costly is that phase of the life cycle, and how maybe some behavioral some behavior either by where they spend most of their time or how much time they spend in group, how that affect this cost might be important. So yeah, I would like to thanks all the the French support organization, IPEV and TAF for the logistic support, Malcolm and Christophe for help in the field, and Mastergate for funding my time at the University of Glasgow this summer.
Well, thank you, Susan. That was great, very interesting. Just check now, see if we have anybody with any questions. If anybody does have a question, if you can please raise your virtual hand, just click the button on the menu, or alternatively you can type it into the questions field. I don't think we have anyone with any questions, but I was just wondering, in terms of the wallowing behaviour, maybe, do you think it might be due to comfort? Maybe the animals actually find the mud soothing and more comfortable during the molt, and that's why they spend most of their time there.
It might be a comfort if it's soothes the process of losing their hair. Maybe that's comforting, or if it just means that they can better regulate their temperature, I would also classify that as being more comfortable. But I think there's a mix of reasons why they use wallow. Comfort might be one of them.
Okay, and well, the other question is, how do you go about basically deploying and recovering the stomach temperature pills? That's quite interesting.
Well, like deploying, you just you use like a tube to push the pill inside, that you go through the yeah, a tube that you put through the stomach and push the pill inside. You don't recover the pill though. You recover the tag that is downloading the data that is on the back of the animal. That's all you can recover, and that will have the data. And the pill, it just like go through the natural process, but usually it's lost. You don't get it back.
I think we might have a question. Hang on a second. Yes, this is from pardon my pronunciation, Nick Van Gel. That is, what was the reason to use DT instead of actual seal temperature?
Because seal body surface temperature will be affected by the temperature of the air. So it's to try to take that into account. So to have a temperature that you can compare between individuals, like the air temperature is colder, like the seal might be colder, and like you just have like a relation between the measurement of the body surface temperature and like air temperature. So just take that into account.
Okay, we also have another question from Dominic. Susan, you mentioned that there was a wide variation in body mass loss that could not be explained by movement. What other factors would influence individual mass loss?
Well, like there might be some individuals that go feeding. That's why we want to put a stomach temperature pill, because we our hypothesis is that they are on land and they're not feeding, but we saw that they move quite a lot. So they could be feeding, and that might explain why some animals lose less body mass. Another explanation is by just reducing the energetic cost by keeping warmer, and that would be by spending more time in big groups, huddling more in colder temperature. So they use less energy to sustain high surface body temperature, and maybe lose less weight per day.
Okay, I think we also have a question from Murray Stark. Murray, I'll just unmute your microphone and you can ask your question of Susan.
Hello there. Yeah, I was wondering, are the seals, while they're molting, are they bothered by flies or biting insects?
Not really. I'm not sure they would feel any of that. They're quite big fat animals, and yeah, it's not something that concerns them. And also there's not that many insects in this region, or much less, I would say, than in tropical region or things like this. It's not something that you see a lot, insect.
I just wondered if that might explain the wallowing.
Yeah, that they put mud around them, and yeah, I wouldn't say that insect bother elephant seals.
Okay, we have another question here. Again, it's from Nick van Gel. In reaction to Dominic's question, perhaps looking at weight loss as a proportion of initial weight may reveal a present pattern.
Yeah, but that's why I only compare individuals that had the same weight at the catching, because like bigger animal will lose more weight than smaller animals. That's usually what happens. And that's why when I compare individuals, I was comparing two individuals that were more or less the same weight at the beginning of the moult. Because then you can compare their behavior and say that there's a difference in body mass loss. You can't say that if you're just looking at all the animals together and not taking into account the mass at the beginning.
Okay, just checking. I don't think we have any other questions. No. If anyone does have any final questions, if you could type them in or raise your hand. No, I think that's it. Don't think anyone else has any questions. Well, thank you very much, Susan. That was a great talk.
Thank you.
And yeah, that was excellent. I'll be in touch shortly. Thank you.
Thanks.